Chapter 1.3, Problem-Solving Procedures. So in this chapter, we're really just going to go through the basics of problem solving. We're going to talk about a procedure you can use to help you solve problems, to utilize some critical thinking, because that's all this class really is about. Now that we've talked a bit more about fractions and percents and all of that, it'll help with some of these problems. But really, the main point is to get down a method so that you're not thrown off by, like, hard word problems or lengthy types of problems or new types of problems that you haven't seen before, stuff like that. Like, figuring out how to start something is the hardest part in a lot of these things, right? So we have this thing called Polya's procedure. So it's named after this guy, George Polya, who was a mathematician back in the 1800s through 1900s. He basically came up with this general procedure for solving problems. Step one, understand the problem, right? I mean, isn't that the hope? But let's talk about exactly what that means. Then devise a plan to solve it, carry out the plan, check the results. So let's see, what exactly does this mean? Let's break this down. Understanding the problem. Start by reading the problem carefully, at least twice. Why do we do this? Because sometimes when you read it the first time, things get missed, right? Or it feels overwhelming because there's a lot of words, right? So we want to be able to just calmly read it a couple times until we really get it, right? Try to make a sketch of the problem, especially if this is a geometry type problem, which we're going to be seeing more of. We want to label any information on there. Getting a visual for a problem can be very helpful. Then we'll make a list of given facts that are pertinent to the problem. That can be very helpful. Even if not all the facts end up getting used, just having like a bulleted list of important things will simplify the problem so you don't have to keep rereading it, right? Then determine if you actually have enough information to solve the problem. If you don't, maybe go back and reread again and see if something's missing. But it might be hard to determine that before you've really thought about your plan for solving. Now, step two, that's devising that plan. So we ask a lot of questions in this step. We want to say, well, can I relate this to something I've solved before, something I've worked on before? Is this similar to another problem? What was the procedure for that one? Can I express it in some algebraic way? So, like we saw with the percents, we're going to see more of those. Like, I can turn that into an algebra problem from, like, a whole word problem. We want to look for any patterns we can see and try to utilize those. Is there a relationship between particular values? Can you express it more simply? So turning it into those simple sentences that then get turned into the algebraic equations is one way of simplifying it. But really it's just, can you cut out all these fancy words and get down to just the bare minimum of what you actually need instead of overwhelming yourself? Can you substitute smaller or simpler numbers to make it more understandable? If the numbers have a lot of decimals in them or something like that, or fractions, whatever, sometimes it's a lot easier if you just replace it with a whole number and work through it that way. Can you do it in your head that way? Sometimes problems can actually be done in your head if it's whole numbers, and so you can get an estimation of what the answer should be if you use numbers that are similar. Then you find the actual answer and you can sort of check. Will listing the information in a table help in solving the problem? Again, this is about organizing things, right? And comparing information. Can you make a guess? This is kind of related to the substituting simpler things, but can you make a guess at the solution? This is a big thing. If we can guess at the solution, we can check our answers easier, right? Because when we talk about checking our answers, which is the fourth step of this one, we're talking about redoing the algebra. What if you make the same mistake twice, right? The same arithmetic mistake twice. You add two numbers together and get it wrong. I do this all the time. But the difference is that I often have an idea what an answer should look like before I even work through the problem. I can look at it and be like, that doesn't look quite right. And that's coming from me making educated guesses at my solution. Word problems, it's a lot easier to do this on because we're talking about real world things. I'm not going to give you a problem where I'm asking how many slices of pizza someone eats and the answer is 3,000, right? That wouldn't make any sense. So clearly something must be wrong if that's the answer you're getting. So that's really the big thing I want you to think about, is checking your answers for reality, right? That's what we want to think about. And making guesses beforehand so you can reference back to what it feels like the answer should be. How many pizza slices does someone eat? Probably less than 10, right? So if you're getting a number higher than 10, maybe you want to check your work. Okay. Step 3 is, of course, going through all of the planning that you did and hoping you get to a good answer, which we then check in step 4, right? Ask yourself, does the answer make sense? Is it reasonable? If the answer is not reasonable, go back and check your method, check your work, check your calculations, all of that. Can you check the solution using the original statement too? Put it back into what was said. This number means what within the context of the problem? Is there an alternative method you could use? In a lot of math, there's more than one method to solve a problem. So if you used one, you can check yourself by using another. Can the results of this problem be used to solve other problems? So that's not necessarily as much of checking the results, but it's checking how useful those results are in the wider problems you're working through. All right, so now we're just going to go through some problem examples, essentially. So, first, shuttle revenue. We've got Airport Express Shuttle Service provides service from San Antonio International Airport to downtown hotels, approximately 10 miles away. One particular shuttle makes 16 round trips per day, carrying 5 passengers per trip. The fare each way is $18. What are the receipts, which means like how much money, come from one day's operation for this particular shuttle? Okay, so when I go through these problems and I'm trying to understand them, I often ask a few questions. I ask, what do we know? What do we need? And then we get to the solving step, the figuring out how to solve it, the plan, right? So to understand it, we want to know, what do we know? And a good thing to do when you're working with a word problem, again, to not overwhelm yourself, is as you're reading it, and remember we want to go over it a second time, as you're reading it, underline anything where there's a number. Okay, so I'm just going to go through, and the number with like units involved, so I know the context of that number. It's also very important. Units, very important. Okay. And then I'll often circle generally what we're looking for, or what the question is, not the whole question. Try to simplify it down. So we're looking for receipts. Okay. For one day. All right. So what do we know? We know all those things I underline. The distance from the airport to the downtown hotels is 10 miles. The number of round trips per day is 16. The number of passengers per trip is 5. The fare each way is $18. What do we need? Total fare received in one day. That's what I circled, right? Okay, now to solve it, what can we do? We're going to need a few things, okay? We want to know the total fare received in one day. Okay, so let's think about this. The total fare received in one day. There's 16 trips per day, 5 passengers per trip, and the fare is $18 each way. So, notice that there's actually one piece of information here that's not going to matter at all. There's no relationship between the miles and any of this, actually. It's not going to come in. Because it's not $18 per mile, it's just $18 total. It doesn't matter how many miles they went. They're paying $18 for those 10 miles. So, one thing we do need to be careful about is that these are round trips. And the fare each way is $18. So, in fact, the round trip would be $36. So, there's like this little tricky part that's a common sort of mistake that could catch you up on, that could hang you up on this. Okay. Now, to figure out the total received each day, we want to take the number of round trips times the number of passengers times the cost per round trip. That'll get us our total. Now, why would that be? Okay, so we've got one passenger. Okay, They're paying $36. Okay, now there's 5 passengers on one bus, right? Or one shuttle. So that's 5 times 36. Each of them pays $36, okay? And then, well, but there's a bunch of shuttles, so there's 5 times 36s times the number of shuttles. Like, that's basically what's happening. So if you can sort of break it down, like, what is one passenger paying? What is one thing doing? And then build it up. So you can work with a much simpler version, right? And then build it up so you can see where these numbers would come from. How would they relate? We're not going to divide, right, to figure out what one person paid. We would multiply. What about 5 people? How much do they pay? We multiply, right? So that's what you want to do. So we multiply. We could just fill these numbers in. Number of round trips, 16. Number of passengers, 5. Cost per round trip, 36. Multiply all that together, it's $2,880 total. Okay. Now let's take a look at a new type of problem where we've got a graph with percents involved and a lot of numbers. There's a lot happening here. So this is about sort of retirement planning. Okay, so we can see in this graph, we're looking at how much you withdraw annually, affecting how long your money will last into retirement. So it's never too early to start planning for retirement, even though retirement's probably a long ways off for a lot of us. The U.S. Census Bureau data indicates that at age 65, the average woman will live another 21 years and the average man will live another 19 years. The data also indicates that about 33% of the average person's retirement income will come from Social Security. When discussing retirement planning, many investment firms and financial planners use the graph in the figure, which shows how long a typical retiree's assets, or nest egg, will last based on the percentage of the assets withdrawn each year. Alright, so here's our questions. If a typical retiree has retirement assets of $500,000, how much can they withdraw annually if they wish the assets to last 21 years? So in this problem, once again, we're going to go through and underline the important numbers. 500,000, 21 years. How much can they withdraw is like the thing we're looking for, withdraw annually. The chart is where all of this comes from. So I just want to look for what information in the chart relates to that. Well, 21 years is part of the chart, right? There's no percents in this problem. There's no dollar amounts in the chart. The only thing I can see relationship-wise is there's that 21 years. So taking a look at that, that seems like it's going to be important. Okay, well, the 21 years says that percent of assets withdrawn annually, 6%. So we want to withdraw 6% of the total assets annually. And once again, thinking about those percents, right? With our withdrawal amount is 6% of the assets, right? Withdrawal is 6% of our assets. So we can fill this in. That 500,000 is our assets. That is our equal sign, right? So, and then we get multiplication. So withdrawal equals 0.06, which is 6%, times 500,000 for a total of $30,000. Okay, similar question. How much should a retiree have in assets if they wish to withdraw $25,000 annually and wish their assets to last 18 years? So this is kind of a reverse. We don't know how much total they have. We want to figure out how much total they would need in order to do this. So it's a different piece of information that's missing. But we're looking at the 18 years here, right? So we go back to the chart. That's 7% we need to be withdrawing. So 7% of the assets should be $25,000. So should be is our is, right? We can write our is, which is our equal sign. It's all the same thing in this case. So 7% is 0.07 times, right, of is times, our assets, which we don't know, that's our unknown, is equal to 25,000. So how do I solve this for the assets? I just have to divide that 0.07 to the other side, right? So 25,000 divided by 0.07 is $357,142.86. So that's how much they would want to retire with if that's their retirement plan. Continuing with a little bit more exploration of percents in these types of problems, we have the cost of Freddie's meal before tax is $28. Isn't that nice? It's a 0.00. When is that ever going to happen? But if a 6.5% sales tax is added to his bill, determine the total cost of the meal including tax. So again, we're going to take this and make it into a simpler sentence that I can then do a direct translation of. So here we have what's important. We've got the 6.5% of added to his bill, determine the total cost. We've got this $28. Our goal is to get total cost. What do we know? Well, the sales tax is 6.5% of the meal. That's not our final answer, but we're going to then add afterward. So I'm going to do this in two parts. I'm going to find the sales tax, and I'm going to add it to get the total cost, okay? So the sales tax is 6.5% of the meal. 6.5%, well, 6.5 is 6.5, right? Moving that decimal over twice, we get 0.065. Our is becomes our equals, our of becomes our times, and we know the meal price is our $28, so its sales tax equals 0.065 times 28, which is then $1.82. So that's how much sales tax we have. Sales tax is added to the price of the bill. So in other words, the total bill is the cost of the meal plus with the sales tax, right? So I just added on top to get 28 plus 182 for total of 29.82. Okay. If Freddie wants to leave a 10% tip on the pre-tax cost of the meal, how much should he leave? Okay. It's a very bad tip, but luckily we know that 10% is easy to calculate, okay? So we're going to start from there. Tip is 10% of the meal. That's what's happening here, right? So the pre-tax cost of the meal is that $28. And now we just fill in. Is our equals, of is our times. 10% is 0.1, right? Because we're moving our decimal over 1, 2, so it's 0.1 times 28 gets us 280, which is just actually moving the decimal over one time is how we get 10% of something, right? So anytime we're multiplying by tens or hundreds or dividing by tens or hundreds, it's just about moving the decimal over, so that's something you can quickly do in your head. So if I wanted a 10%, like to find 10%, I move the decimal over one time. 28, move it over once to 280. Okay, so if I then wanted to get a 15% tip, I could use that, but we'll get back to that. The tip is 15% of the meal. Same problem. I get 0.15 times 28 for 420, but an easier way to do this, a simplified way to do this, and the reason I'm doing this problem is just as a hint for when you're calculating tax. To find 15%, we find 10% and add half of that amount. So 280 plus half of 280 is 140, you get 420. Now, if we wanted to get 20% tip, it's 2 times 10%, because 20 is 2 times 10. So I'd take 280, multiply by 2, so 20% tip would be 280 times 2 for a total of 560. Right? So we can do this a little bit quicker when you're at dinner and need to calculate a tip. If you're a 20% tipper, you just got to find that 10% by moving the decimal over and then double it. Boom. And so we can kind of do that fairly quickly, even maybe in your head, instead of worrying about doing a big calculation. All right. Our last problem is working with solutions, and this is going to bring in proportional reasoning, which we'll see a bit more in our geometry chapter. Some recipes for smoking a turkey recommend pre-soaking the turkey in a brine solution. To make enough brine solution to smoke a 12-pound turkey, use 16 tablespoons of salt in 2 gallons of water. Okay, so I'm going to underline, there's 3 pieces of information here. 12-pound turkey, 16 tablespoons of salt, and 2 gallons of water, right? Okay, so that's 3 numerical pieces of information. When we're working with proportional reasoning, which I'll get into exactly what that means in a moment, but essentially you're going to be looking for these information about different units related to each other in some way within the same sort of object or something like that. So in this case, cooking a turkey, this turkey has these 3 facts about it. And then we scale that in some way. So if you wish to make 3.5 gallons of brine solution, how much salt is needed? So we're scaling the amount of solution in this case. So we have our number of gallons is our gallons of water we work from. So we're going to set up this proportion where we're relating our gallons of water to our salt. That's the only thing that matters here. The amount of turkey doesn't matter because the turkey isn't part of the question. Okay, so relate the salt to the water. When I create what is called a proportion, I have a given ratio and a ratio that involves an unknown and a known value. Okay, the given ratio is the 16 tablespoons of salt versus the 2 gallons. Does it matter which is on top, bottom? No, it doesn't. I like having the thing that is being asked about, the unit that is being asked about on the top, but it doesn't really matter. You'll get the same answer either way. Okay, so we're being asked about how much salt. We are given a number of gallons. So the unknown is the tablespoons of salt. The known for the information for this question is a number of gallons. Notice that I line up my units, right? Gallons to gallons, tablespoons to tablespoons. Given information, unknown with the sort of known value that's part of the question. So they're paired together, units across from each other. Okay, to solve a problem like this, we use what's called cross multiplication. Okay, cross multiplying means we multiply diagonally, but essentially what you're doing is you're multiplying by the reciprocal, and there's a whole bunch of stuff that's happening that causes the cross multiplication to work. So you multiply by their denominators, and then you divide, and yada yada yada. But we can quicken this process by multiplying diagonally. So 16 times 3.5 is equal to 2 times x when I do this. Okay? And notice that I replaced my question mark with an x here so that I have a variable to work with. But that's all the x means. This is just our question mark in the problem. Okay, so cross multiply. Now simplify that. 56 equals 2x. To solve for x, I divide by 2, right? I want to get rid of this 2, so I divide both sides by 2, and I get x is 28. So in other words, we don't just end it there. We don't just say 28. No, we want units. Always use your units when it's relevant. 28 tablespoons of salt. Okay, so we've been able to scale this solution up to work for a larger amount of water, a larger amount of brine solution, right? Okay, what about if we have a larger turkey instead? How much salt will be needed for a 20-pound turkey? So in this case, I'm going to be comparing new information. I don't care about the amount of water. I'm just wondering how much salt and how much turkey. So here, the 12-pound turkey versus the 16 tablespoons of salt, those are going to be paired together as my given information. But my known is now the turkey. I have this 20-pound turkey. What amount of salt is paired with it? That's my question mark. So I put 16 tablespoons over 12 pounds, question mark tablespoons over 20 pounds, right? Now I cross multiply again using an x in place of that question mark. 16 times 20 equals 12 times x, right? Again, same thing. Then I have to divide out that 12 to solve. So divide by 12 on both sides to get 320 over 12 is approximately 26.67. But again, we want to give our answer with proper units. So it's 26.67 tablespoons of salt. So this is a really useful technique to be able to figure out recipes. Like if you need to scale a recipe, this is exactly how you would do it. Like if a recipe calls for 24 cookies and you need 36 of them, what do? You have to do stuff like this on each of the ingredients. So this isn't just like a math problem you're seeing in class. This is something that you can do in real world cooking, right?